worst case, you can take your own computer, but it's easier.
Anything is negligible. Okay. So let me just connect to the Wi-Fi if I'm not already connected. Okay, so let's see.
Yeah, it's written here.
Should they come up or should
See.
No,
Yes.
no, not to that place.
Dash beyond.fr.
Yeah.
right now? Dominic?
Okay, no, I know. Where are you?
I'm in Germany.
Which place?
Ingolstadt. It's a small place. But
Is the other author your student?
no, this collaborator said he's also around here.
How you apply it?
Do you
Called
usually come to Gold?
I'm they published more in math things. I mean, it's my second book paper. I had one
Okay,
2 years ago.
Yes.
Okay. So first one, yeah, the first one. Yeah.
Let's just
We
go
should
ahead.
get started. Yeah.
Test. Okay.
Okay, so good morning, everyone. Welcome to the session on non-convex optimization. The first talk is by Dominic Stuger, and it's on non-convex matrix sensing, breaking the quadratic rank barrier.
So, yeah, hi everyone. So I'm Dominic, and this is joint work with Yizhe Xu, who's also around here. So yeah, this talk is about low-rank matrix recovery, and to think of some example of low-rank matrix recovery, think of matrix completion, where you're giving a few entries of an unknown matrix, which is low rank, and you try to complete this matrix. And I mean, low-rank matrix recovery, of course, appears in many other applications, like say phase retrieval, robust PCA, and blind deconvolution. And so now let me formally describe the problem setting. So we're given linear observations yi, which so there's an unknown ground truth matrix X star, which is low rank, say has rank R, and we're given linear observations yi, which is say the trace inner product of a measurement matrix AI with X star, and so the AI, of course, are known measurement matrices. And then our goal is we try to estimate the matrix, the unknown matrix X star from these observations. So, and basically now if you look at the literature, there have broadly been two approaches studied for this problem. So the first, I would say really two classes of approaches. So the first class of approaches are convex approaches. So what are we doing here? So here, typically we're solving a convex problem. Say we try to solve a norm minimization, a nuclear norm minimization, where we try to find the matrix of smallest nuclear norm which satisfies our observations. And the nuclear norm here is just the sum of the singular values. And I mean, if you look at the literature, I mean, there are pros and cons of this approach. I mean, the pro is it's theoretically basically well understood. We know this approach basically with near optimal sample complexity, we can reconstruct the unknown ground truth matrix. So with approximately, say, up to log factors R times D measurements, which is yeah, more or less what the information theoretically is optimal. But the disadvantage, of course, is nuclear non-minimization. I mean, it's an SDP, it's computationally expensive, and so it's not really what we want to do. And there are non-convex approaches in the literature, say, where we write a non-convex objective, which they say is based on matrix factorization, where we have U and V, which are D times R matrices, so we have less optimization variables, and it gets computationally more expensive. However, this is the advantage. However, the disadvantage of these approaches is the theoretical guarantees which are known for this are basically much weaker. In particular, what we want to focus on in this talk is what we know about the sample complexities is typically much weaker. In particular, we need basically all existing guarantees need R squared times D samples, right? And this is compared to R times D, which we have in the convex case. And so the question is, right, is this additional R factor really necessary? Is this an artifact of the proof, or can we do it with R times D, or is it just so? Right, what is this? And if you look now at the R times D factor, I mean, of course, there's a huge literature on non-convex optimization with matrix factorization, and I mean, here I've listed some papers, and if you go through all these papers, I mean, you see everywhere there's the sample complexity R squared times D. So this is really, I would say, a fundamental problem in the literature, where you have this additional R factor in the sample complexity, and the question is, do we need it? Oops. So yes, and this is what we want to focus on in this paper. What we focused on in our paper is the question, can we get recovery guarantees for non-convex method, which actually have linearly dependence on the sample complexity in the rank? So let me just describe our samples, setting, which we still have in this paper. So we have samples yi, which are some matrix X. We have inner product X star with measurement matrices II, and for this talk, we assume that the matrices X star are PSD matrices, okay? The AIs, we just say they are Gaussian measurement matrices. And then for the talk, we need the condition number kappa. Okay, and so this is the setting. And then in this paper, we just take a two-stage approach, which is which has been very well studied in the literature. But I mean, we want to understand whether we can get rid of this R factor, which has always been there. So this two-stage approach, we have two phases. So the first phase is we do a spectral initialization. So we form some matrix A star Y. And then we just take the truncated rank R SVD, and we factorize it, and we get a factor U0, which is our first guess for our, which we take then as initialization for the second step. And I mean, of course, the initialization is that if you take the sample size large enough, or the intuition is that if you take the sample size large enough, the spectral initialization should be somewhat be a good guess for our ground truth matrix. Yes. And then in the second step, we take our non-convex objective function, and here, because we're symmetric, right, I just have one factor, I have just a factor u, and I can write it UU transposed, and then on this non-convex objective, I just run gradient descent. Okay, so it's just two stages, spectral initialization, gradient descent as usual, and then the question is, can we improve the sample complexity? And then the answer in our paper is yes, we can get rid of this additional R factor. So we have, so what's the theorem? So we have the ground truth matrix X star, which, because it's rank R, I write as U star transpose. Then, I mean, of course, I can only recover U star up to some rotation, so this is why I need to introduce some notion of distance, where I take, essentially, where I modulo the rotation. And then what does our theorem say? So we have Gaussian measurement with sample size m larger than R times D times kappa squared. So the important thing here is that this is now linear in R. And of course, okay, this has a sample dependence on the condition number kappa squared, but this is also there in all previous work, basically. And okay, we have some assumption of step size. And then with this assumption, we can show that now the iterates converge linearly to the ground truth. And this means we have a recovery guarantee which scales linearly in the rank. Okay? And I mean, this is a first step to improve this results, but of course there are open problems remain. So one is, this is now the PSD setting, and we would like to generalize this to asymmetric ground truth matrices. We have 1 over kappa in the step size, which is not needed if you run it empirically. And then you can ask, do you need the quadratic dependence on the sample complexity kappa in the final result? And then, of course, this is now for Gaussian measurement matrices, but in practice you probably want to have rather rank 1 measurement matrices. So say, like in matrix completion and so forth. So these are kind of the open problems which remains. And I should say 1 and 2 have just been solved a week ago in a follow-up work. I mean, they haven't studied vanilla gradient descent as we do in this paper, but Riemannian gradient descent. But in a follow-up work, this has been actually solved. Okay, then let me briefly talk about the proof ideas in the last 3 minutes. So typically how you study these problems is you have the gradient, and I mean the gradient is a random object because your measurements are random. So what you do is you decompose the gradient in an expectation part plus some deviation part, and you try to show that the deviation is small. And for this, you need to control, you need to control some term, but basically the problem, which I wrote down here, but the precise formula is not important, but the problem is since you run gradient descent on a random loss function, your iterates, U0, U1, U and so forth, they depend in some complicated way on the measurements. So if you want to bound this, you cannot just apply standard concentration inequalities, but you rather need to do some uniform bound or something, right? But the problem is if you establish a uniform bound, you actually get this R² factor. And as we show in our paper, this bound is optimal, so uniform bounds. With uniform bounds, you cannot get optimal sample complexity. But you don't need uniform bounds. Of course, you just need to have some bounds over the trajectory. And how did we make this how did we get bounds over this trajectory? So the key proof technique which we introduced in our paper were basically virtual sequences. This is in some sense related to what people did with leaf one out sequences, but what we really did is we run virtual sequences where we disturb the measurements over some epsilon net, and then basically we are able to weakly decouple the sequence, so the gradient descent sequence from the measurements, and with this additional statistical freedom, we're basically able to establish stronger concentration bounds, and with this, we are able to prove what we need to. Yeah, and with this, I'm at the end of my talk, so thank you.
Regarding open problem 3, the dependence on kappa, do you have any intuition what the dependence should be?
I basically think you get convergence with R times D, but maybe not linear convergence of,
But independent of kappa?
Yes. So I think you will get, if you have R times D, we will always get convergence, but maybe, say if you're in this regime between RD and RD times kappa squared, I think it's maybe slower. So that would be my intuition.
Okay, thanks. Other questions?
Thank you for the talk. I have a question. How do you choose the rank R of the non-convex problem, and in practice, does increasing this rank R improve? Does removing the rank R delete all the local minima or not?
So in this work, we have assumed that the rank is known. So basically, the rank of the ground proof is known, and then we just choose the same rank. In practice, you choose R probably a little bit larger, you overestimate it, and then you still converge. And I basically believe that our techniques would also generalize to this setting. So I think this can be generalized to a setting where, say, you overestimate the rank a little bit.
Okay, so maybe while the next speaker sets up, we can take one more quick question.
Thank you for the talk. So it seems to me if you apply the uniform bound along the path, then the path is dependent on kappa, so that the kappa dependence is unavoidable. Could you explain the intuition for why you think kappa dependence can be removed?
So the kappa dependence comes from the spectral initialization, basically. So if you're below RD kappa squared a little bit, the spectral initialization will not be that good. So this is basically the reason. Yeah.
So that means you think the kappa dependence is necessary?
Well, I think basically you will converge also below, with less sample. If you're between RD and RD kappa squared, you will also converge, but we can take this offline, but yeah.
Okay, so let's thank the speaker again. Okay, so the next talk is by Wanzhen Zhao on the adaptive complexity of finding a stationary point.
Thank you for introduction. Hello everyone, I'm Wanzhen Zhou from the University of Tokyo and Likan IP. And this is a joint work with Andy Han and Akiko Takeda, Masashi Sugiyama. And first I will go overview, and firstly I will introduce some background and then some summary of main results and some results in high dimensions, constant dimensions, and finally I will give a conclusion and open problems. Firstly is the background, and we consider parallel non-convex optimization. The goal is to find the station point of non-convex and a smooth function f, and in other words, the gradient norm is small enough. And the main difference compared to query complexity is that the oracle is parallel. In other words, in every round, you can query many points, and the parallel first oracle will answer the function value of these queries and the gradient value of these queries. And the adaptive complexity means how many numbers are required to, how many sequence rounds are needed to draw a station point. And the question is that whether parallel oracle can accelerate the non-convex optimization. And then I give some results. The first result is in high dimensions when D is larger enough. And for high dimension case, and D is larger than epsilon to the negative of 2p plus 2 over p, and with p order smoothness. And the existing results shows that ARP, including gradient descent when p equal to 1, and Newton's method when p equal to 2. And this method has been shown is optimal and by some query complexity. And in our results, we show even with parallel polynomial D queries per round, and the ARP and including gradient descent, Newton's method are adaptive optimal. And we give a slogan like this: parallel offers no acceleration for high dimension non-convex optimization. And also, our results can be viewed as a stochastic case with sigma, the variance sigma as 0. And the stochastic gradient descent has been shown query optimal. And the existing adaptive complexity show when sigma is large and it's optimal. And in our results, we show adaptive combined with large variance, and combined with our results with sigma equal to 0, and which implies the correct answer of stochastic non-convex optimization is like this, which means SGD is optimal. And we also give a slogan like this: parallel offers no acceleration for high-dimensional stochastic non-convex optimization. Then when does parallel accelerate non-convex optimization? And we show low dimension case, we can accelerate. In constant dimensions, which means D is constant, and we consider bounding case, since you can easily reduce the unbounded case to bounded case. Existing results shows in one round and many, you just naively query all the grades of with some gap of the grades like epsilon, and you can find the station point in one round, but with many queries. And the recent work, gradient flow trapping, shows in log 1 over epsilon rounds, you can find the station point. And our results bridge these two methods by showing constant rounds how many queries are required per round. And we also show some lower bound by showing this gradient flow trapping are adaptive optimal. Then there is also two slogans, and the parallel axis is constant dimensional non-convex optimization, and the gradient flow trapping and its variants are adaptive optimal. Then I give some technical details about high-dimension case and the constant case. Firstly is I'll give a recap about query complexity for finding single point. And common is then the robust training function parameterized by an orthogonal matrix like this. And this training function satisfies three properties. And by combining these three properties, we can show in each round you can only find one part of the orthogonal metric. And why does this argument break down in parallel settings, since it relies on the projection on the queried vectors and the discovered orthogonal vectors. And in our method, we use the random projection to some random partition of the coordinates. Specifically, we consider a random partition construct like this, and a quantity xi like this, and we construct the training function satisfies these three properties. And we can show by concentration bound of conditional Bernoulli random variables, and we can show in each round you can only find one part of this random partition, and then similar argument applies. Then I talk about some constant dimension case. And for constant dimension case, we give a characterization of the decision point, which means if for some region, if all points on the boundary cannot reachable for the start point x, then there must be some decision point in this region. Then the goal is reduced to finding a domain with a small enough diagram that which its boundary is all unreachable. And we propose a gradient flow gradient trapping like this. In each round, we first identify some, we query a dense enough barriers in some region, and then identify the smallest points in this. And we can claim the xt plus 1 is some mass contained in some region whose boundary are unreachable. Then we compress the domain small enough, and we can show our algorithm can compress this in constant rounds. Then we complete this result with some lower bound. The lower bound is proved by some reduction, by reduce the finding central point to finding a local minima of the monotone pace on the grid graph. And there exists some lower bound for finding local minima of monotone pace of a grid graph. So we combine this reduction and the lower bound in that case, and we got the lower bound. And we show our algorithm are optimal. Finally, we could give some conclusion and open problem. For constant dimension, we show gradient flow and its variants are adaptive optimal. For high dimension case, we show ARP, including gradient descent, Newton's method are optimal. Then the open problem is what about intermediate region? Thanks for attention. Any problems? Questions?
Thank you for the talk. So when you say you have lower bounds for high dimensional algorithm and low dimensional algorithm, so what are the algorithm class that it applies to? So are they the same algorithm class? I guess for high dimension it's a zero respecting algorithm maybe, but for low dimension, what is the algorithm class?
Sorry, could you repeat it?
Okay, so you have two lower bounds.
Yes.
One for high dimension problems, the other for low dimension problems.
Yes.
So what kind of algorithm does the lower bound apply to? So what is the assumption on the algorithm class for these two cases?
Just smoothness.
I mean the algorithm class.
For low dimension, we just assume it's beta smooth, and for high dimension, we assume it's p smooth, p order smoothness.
Okay, we can take this offline.
Thank you for the question.
Other questions? Now let's thank the speaker again. So the next talk is on data selection for ERMs by Alexander Shmilovich. Sorry.
Hi everyone. So this is our joint work with Steve Henneke, Shai Moran, and Mérieux. And it is on data selection for empirical risk minimizers, as was said already. And so let's start from trying to understand why should we do that selection. Okay. So at a high level, learning can be viewed as a union of two parts, algorithm and data that we train on this algorithm. So most of the research in the last couple of decades was mostly focused around algorithms, how we should construct new algorithms, how we should improve different algorithms. And most of the time, data was viewed like something that was either fixed or under some very strong constraints on it. In this work, we take a complementary approach, and we try to study data selection with a fixed and natural algorithm. As Andrew Yang said, improving data often improves performance more than tweaking the model. So let's try to understand how we can improve our performance using the data. So the framework we study is highly theoretical, and let me just describe it step by step. So we have a data set D, and we have a learning algorithm A, and we try to use fixed and natural learning algorithm, and in our case, we will use mostly empirical risk minimizers. And so in the between of data set and the learning algorithm, we have a teacher, and the teacher knows everything about data set and knows everything about learning algorithm. And the goal of the teacher is to provide a data set of a fixed size k to our learner in such a way that its performance will be the best possible. This setting can be viewed as some version of a machine teaching. And in order to understand how does our algorithm perform, we will look at teacher's goal to minimize the loss on the entire data set. Let me stress out that we consider the data set our total distribution, so we do not have any underlying prior distribution. The whole data that we have is observed in our data set. Okay. So we studied this question across different possible settings, starting from mean estimation, which will be the most basic case in this setting, and also classification tasks, both in general binary classification and in linear classification. Also, we studied linear regression, and we also gave some results for general stochastic convex optimization. Okay, so let me briefly tell you about overview of our results. So we basically studied in linear case, we gave some optimal bounds, and in general classes, we gave some near optimal bounds for classification. In linear regression, we tried to find some optimal bounds for different values of k, but for some cases, we still have open questions, and we will discuss them tomorrow. So I invite you to come to our open problem session tomorrow. Also, for stochastic convex optimization, we found out what are constraints and conditions we need in order to successfully classify data. And for mean estimation, we will dive into mean estimation now. This will be an example that I will show you. So let's start with it. Okay, let me define everything once again on the mean estimation case. So we have a data set D. This data set consists of points from R. And we will select some subset, actually not subset, it is multiset from D. So we can select any k points from our data set D. And yeah, before we understand what to do with this subdata set S, so let's first understand. So we have a loss. This is a natural loss for the problem of mean estimation because mean of the whole data set minimizes it. And yeah, optimal loss will be equal to the value of this loss on this minimizer and will be lowest among all possible points in R. Okay, what does our algorithm actually do? So we have an algorithm A, and generally just averages points from selected set S. This happens because in order to minimize the empirical risk on our loss, if we only look on it on our subdata set, this is exactly the solution for it. And the value we're interested in is this long formula at the end of the slide, which is minimal over all possible such subdata set, such multisets drawn from D of size k, of loss of algorithms that we computed on this data set. And since our algorithm will just provide us with mean of points that we selected in our S, then what we are actually trying to minimize is just the loss on the entire data set D of mean of our points that we selected. Oops, no. Yep. Okay, yes, so, yeah, so this is, so generally we ask the question, how close can we get with LD star of k to the minimal loss of LD star given by the optimal solution, which is given by mean of the entire data set. And actually we found out that this loss can be bounded as a ratio of LD star of k and LD. And in the worst possible case, it will be 2k over 2k minus 1. So it means that for any data set D, we can always select a subdata set S such that the best loss, which is given by the subdata set S, will be not more than 2k divided by 2k minus 1 times more than the one that's given by the best value, which is given by average of this data set. Okay, great. Okay, so yeah, let me briefly introduce a tool that we use during our work. So first of all, I will need to define classical Cartesian theorem. So if we have a data set in RD consisting of some points in RD, and we have a point inside the convex combination of, so actually inside the convex hull of this data set, then we can select d plus 1 points in this data set such that these d plus 1 points will be having this point from convex combination inside their convex hull. So we can reduce our data set to just d plus 1 points and still contain the same convex combinations that we had before. And in our work, we came up with some convex generalization of this theorem for convex functions. So I will now try to introduce it to you. Okay, so yeah, at the beginning we have instead of points in RD, we have functions from RD to R, and they are strictly convex. And we have also convex combinations of this function. Okay, we can think of it as just, for example, as a mean of these functions. Then we can prove that we can select just d plus one of those functions, such that this convex combination, such that we also can select a convex combination of these functions in such a way that minimizer of this convex combination will be the same as the minimizer for the original combination. So in original setting, we were able to select points such that we will have the same point in our convex combination. In this setting, we can select functions such that we have the same minimizer. But this is not the only thing that we have in this convex generalization. We also have a property that we can control the value of at this minimizer. So we can always have that the minimizer, that value at the minimizer of our new convex combination will be smaller than or equal than it was before in original combination. Okay, and to finish this out, let me tell a little about open problems, and once again invite you to join us tomorrow on open session. So tomorrow I will give a talk about some open problems that we had in this setting, and one of them is about mean estimation. So actually we don't have a complete classification for higher dimensions than n equals 1, and just to tease you, I will say that for k equals 2, there is no difference in this result between 1 dimension and 2 dimensions. But as dimension goes to infinity, it should increase to a different value. And for linear regression, we also have some blind spots for some intermediate values of k. And it is also interesting how to complete this gap. So with it, I will end. So thank you for your attention.
Questions?
Hi, thanks. Really interesting problem space. So if I'm understanding correctly, the set of problems you're looking at right now are ones where your learner here on the right-hand side is essentially just a naive ERM algorithm, which is already a really interesting question, but I wondered if you'd looked at all at the question of sort of co-design of the selection and the learner. Are there situations where picking a different, sort of more bizarre learner could actually get us an advantage, or can you already say very easily that that's not advantageous?
So thank you for the question. I think that, so depending on the learner, really all these results in bound can really depend, and in some sense, these results constructed for this particular learners. So for sure, for different kind of learner, it can be that the result will differ a lot.
So it's an interesting model. So if I understand correctly, okay, the learner, we know the learner, and the algorithm is deciding which subset to give to the learner.
Right.
Now another strategy is just for the teacher to run the learner himself on the full data, and then send the answer, instead of sort of sending the answer indirectly through a data set for which it produces almost the same thing. So are there any models in which you really distinguish between those two different strategies? Like, I know that that's not allowed in your setting, but what would be the criteria by which, we prefer sending data rather than just the answer? Because it's sort of implicit in the things you're doing anyways.
Yeah, it's a great question, and it is a valid way of thinking about it. In this particular case, if we will just we're able to send the answers, then most of the times we'll be able to provide one or the minimal amount that's required to fix the learner number of data points. And so we didn't really consider here studying this type of question, but I think it also kind of it needs more specification in order to find some interesting questions there.
Well, maybe the next speaker sets up. Oh.
Okay.
Yeah. Hi. Thanks for the talk. I want to ask whether your results imply actually an algorithm, a data selection algorithm. Are they constructive? Because it seemed in the like generalized Carateri theorem for convex functions, it's probably an infinite dimensional problem to solve, to find these functions. So is there some way to implement this?
Yeah, right. So this construction doesn't apply algorithm. So we were more thinking about it as if some theoretical bound that you cannot overcome generally. So some value that kind of shows you how bad it can get for this particular selection, for this particular budget of points you select.
Thanks.
Maybe the next speaker can set up, and well, I can ask a quick question. So, does it become any easier if you're allowed to weight the points?
Yeah, and actually for linear regression, we studied the setting when we allowed weighting the points, because like if you don't allow weighting the points there, it becomes much more complicated. It's still interesting, but we don't have any particular results in this case.
Thank you. Let's thank the speaker again. So the last talk of the session is by Elisabetta Konakia, and it's on low-dimensional functions are efficiently learnable under randomly biased distributions.
Okay, hello, can you hear me? Okay. Yeah, so I'm Elisabetta, and I'm going to present some joint work with Dan Mikulincer and Helkanan Mossel. So the motivation for considering low-dimensional functions comes from the classical observation that natural learning tasks, even if they are high-dimensional, they often lie on a latent low-dimensional manifold, and this has been observed in several works, and it's conjectured to be at the core of the success of deep learning algorithms. So the questions that motivate this work is, can we show that if we learn with gradient descent on neural networks, then any low-dimensional functions is easy to learn, at least for most input distribution in most settings. So we do know that there are some low-dimensional functions that are challenges, but can we prove that those are somehow rare and not common in some sense? So to be more specific, we consider standard supervised learning settings, where we have training data. There are pairs. The inputs X's are sampled from an input from a input distribution D, and where we have a target function f that maps inputs to labels. And so in this talk, I'm going to be interested in learning this mapping with a shallow neural network, so with ReLU activation, trained by standard gradient descent algorithms, with the goal of performing well at least on data that are sampled from the train distribution. And we release a bit this framework in the sense that instead of assuming that the input distribution D is fixed, it is like well-defined, we introduce some randomness in the input distribution by assuming that it is sampled from some sort of meta distributions over the input distributions. And so the main message that we want to convey is the following. We want to show that if, by introducing this sort of uncertainty in the data distribution, then any low-dimensional target function become easy to learn, and in particular, independently on the target function itself. So in some sense, the low dimensionality is what matters here. So we prove this on like specific classes of models. The first one are Gaussian single index models, and the second one are sparse Boolean functions or juntas. There is a line of works that related to this, which are the ones that concern the framework of smoothed analysis that interpolates between worst case analysis and average case analysis by looking at the average performance on algorithms on some smoothing of the data. and there are some works on in several settings. Here we are particularly interested in adapting this philosophy to the setting of learning with neural networks trained by gradient descent, and we want some quantitative guarantees on the runtime complexity and sample complexity. So let me start with the first class of model that we consider. So single index models are those where the label depends on the input only through a projection on one relevant direction, W, and through a link function, G, which is just a real function. This is a very popular class of model. It has been extensively analyzed, especially on Gaussian isotropic data. And it has been shown that on Gaussian isotropic data, the sample complexity depends on the link function G through a quantity that is called the information exponent, this quantity J. Then in particular depends on the Hermite coefficient of G, and in particular is the minimum order J that is non-zero, and such that the relative Hermite coefficient of G is also non-zero. So in other words, if we fix our data distribution to be the Gaussian isotropic, then there are some easy settings and some more challenging settings that depend on the Hermite expansion of the link function G. There has been some recent work on that kind of departed from the online nature of SGD, so that show that if we allow our algorithm to reuse batches, then the information exponent complexity can be overcome. And here we want to keep the online nature, so we don't want to perturb the algorithmic part, but we want to perturb the input distribution beyond the Gaussian isotropic data. And okay, so the perturbation that we consider is in the form of random shift in the first moment. So we first sample mu from, by simplicity, we assume to be Gaussian. And then fixing mu, we sample each input with still identity covariance, but with randomly shifted with mean mu. And what we can prove is the following. So if we need some assumption on G, we need to satisfy some nonlinearity and some smoothness assumption. And then with high probability over this random shift mu, we can prove some sample complexity guarantees of D cube for basically every G that satisfy these two assumptions. So in other words, we can have a sample complexity that does not depend on our target function G. This means that the Gaussian isotropic picture is sensitive to perturbations in the first moment of the distribution. There was also some work that showed that also perturbing the second moment can break the information exponent complexity. I think an important point of this theorem is that the bound is uniform across all G that satisfy these two assumptions, and also it is with high probability over the shift mu. So in other words, if our data, instead of being centered, if it is consistently shifted towards almost any direction, then we can have these complexity guarantees. Quick idea of the proof. If we look at the impact of the shift on the target function, so if we write x as z, which is an isotropic Gaussian plus the mean mu, then the contribution from WT mu is just a Gaussian contribution with variance 1 if W is normalized, which means that the overall effect of shift in the first moment consists in introducing a shift in the target function. So G is replaced by GQ star. And so the main technical part of the proof is that showing that with high probability over this Q star, the first Hermite coefficient of GQ star is large. So in other words, the information exponent of this shifted function is 1 with high probability. And this involves doing an analytic extension of G on the complex plane and then using some small ball estimates to obtain this high probability bound. And then the second step consists of showing that SGD-like algorithms can use this guarantee given by step 1 to efficiently learn on shifted inputs. Okay, so we also prove a similar result for sparse Boolean functions. These are functions where the low dimensionality is expressed in terms of number of relevant coordinates. So basically, we assume that the target depends only on a small set of coordinates of constant size. Similarly to before, there is some works that consider uniform inputs and show that the complexity depends on f, in particular on the leap complexity, which is a measure that depends on the Fourier-Walsh coefficients of f. And so we again consider a perturbation, again in terms of shift of the first moment, by assuming that the coordinates are still ±1, but instead of being +1 with probability half, they are +1 probability around half by some standard deviation eta. And we can prove some guarantees that scale linearly in D and exponentially in eta. So here we can control also how the complexity scales as the shift increases, and show, as in this picture, that as the shift increases, the algorithm converges faster. And which means that if eta is constant, then we have a linear sample complexity, and also that randomness is important. So if eta goes to 0, then this bound becomes meaningless. So to wrap up, what we show is that Gaussian single-index models and sparse Boolean functions are efficiently learnable with a probability over random, if we introduce random shifts. And this suggests that in the presence of low-dimensional structure, at least in the cases that we considered, hard function seems to be rare and not robust to these like small shifts. And for future work, it would be interested to consider low-dimensional settings where the low-dimensionality is not in the target function, but maybe in the input distribution by introducing some correlation among coordinates. Thank you.
Questions?
Yeah, so when you say with high probability, do you mean in the high dimension asymptotics, the probability goes to 1? Is that what a high probability means?
No, it's with high probability over the shift mu.
No, I understand, but what is high? What's the definition of high?
So that, sorry, I don't see also, but, okay. Yes, so, for instance, this part, yes?
Yeah, so when you say high probability, the word high, what is the formal definition of it?
That probability goes to 1 is 1, it's like the set of PIs here that do not satisfy this theorem as measure 0.
It's literally measure 0, or the measure goes to 0 in some particular asymptotic?
Yeah, it's dimensionless, it's measure 0.
Thank you for the talk. I had a question about your proof idea for the Gaussian case, where you argued that this W times mu gets to a Gaussian, like a small Gaussian perturbation of your target function. But at the end of the day, don't you have an issue where you differentiate according to W? So like technically, this Q star is not going to stay constant across your trajectory, is it?
So Q star is the shift in the teacher. So this is going to stay constant. The shift of the student doesn't stay constant, but with a two-layer network, you can correct for it, and like you do not add the fixed points, basically.
Okay.
But the Q star is the one of the teacher. So.
Okay, thank you.
Is there a hidden dependence on the property of the function g in the sample complexity? For example, if the g is very flat and you just introduce some perturbation, I guess there would be some.
Yes, so it will not affect the exponent, but in the exponent tree, but the constant term will depend on the Lipschitz net bound that we put and also on the nonlinearity assumptions, yes.
One last question.
Okay, I've also got a question about the sample complexity. So it's d cubed But you say it's the first, like if you introduce a shift, it's the first Hermite coefficients, which really becomes.
Yeah.
And the intuition would be for me rather that it's just linear in D then.
Yeah, so there are two things that are not tied. I mean, okay, the D would be the minimum you can have. So we use rel activation, which is not optimal, with like a smoothed activation function, which this could be reduced to D square. Yeah. And also, in order D, we can strongly learn the relevant direction, but we need other D to learn the target the link function G with a parametric model.
Okay, thank you.
But yes, it's the same as the information exponent 1. Like it's just in this setting, it's what we think.
Okay, so let's thank the speaker again. And just a round of applause for all the speakers in this session, and we have a break right now.